Overview and definition of autonomous driving system. An automated driving system is a vehicle automation system that assumes all real-time driving functions necessary to drive a ground-based vehicle without real-time input from a human operator. The automated driving system is generally an integrated package of individual automated systems operating in concert. Automated driving implies that any human sitting in the driver's seat has transferred all real-time driving functions to the vehicle automation system. It is a complex combination of various components that can be defined as systems where perception, decision-making, and operation of the automobile are performed by electronics and machinery instead of a human driver, and as the introduction of automation into road traffic. Autonomous cars use various kinds of technologies. They can be built with GPS sensing knowledge to help with navigation. They may use sensors and other equipment to avoid collisions. They also have the ability to use a range of technology known as augmented reality, where a vehicle displays information to drivers in new and innovative ways. Working of autonomous driving system mainly explained with 4 components, like mapping and localization, obstacle and avoidance, path planning and global positioning system. Working of autonomous driving system. Mapping and localization. Before making any navigation decisions, the vehicle must first build a map of its environment and precisely localize itself within that map. Laser rangefinders and cameras are mainly used for this. To know your location, and being able to navigate to other locations, is extremely important for autonomous robots. The act of finding one's location against a map is known as localization. Obstacle and avoidance. A vehicle's internal map includes the current and predicted location of all static and moving obstacles in its vicinity. Obstacle avoidance is one of the essential technologies in local path planning and one of the critical technologies that guarantee human and vehicle safety. To avoid collision with obstacles, a robot needs not only to detect obstacles but also to recalculate the detouring path and to steer itself toward a safe and efficient path in real time. Path planning. The goal of path planning is to use the information captured in the vehicle's map to safely direct the vehicle to its destination while avoiding obstacles and following the rules of the road. By this, you will be able to find the shortest path over a graph or road network. This course will give you the ability to construct a full self-driving planning solution, to take you from home to work while behaving like a typical driving and keeping the vehicle safe at all times. Global Positioning System. An autonomous car navigation system based on Global Positioning System is a new and promising technology, which uses real-time geographical data received from several GPS satellites to calculate longitude, latitude, speed, and course to help navigate a car. The goal of the project is to make an auto-navigational car model that can route through known or pre-programmed coordinates autonomously without any control by a human. The driverless car features an advanced, highly autonomous drive control system with an anti-drift. Levels of autonomous driving system. In level 0, there is no driving automation. In level 1, there will be driver assistance. In Level 2, there is partial driving automation. In Level 3, there will be conditional driving automation. In Level 4, there will be high driving automation. In Level 5, there is full driving automation. Levels of autonomous driving system. Level 0 is no driving automation. Most vehicles on the road today are Level 0, manually controlled. The human provides the dynamic driving task, although there may be systems in place to help the driver. An example would be the emergency braking system. Since it technically doesn't drive the vehicle, it does not qualify as automation. Level 1 is driver assistance. This is the lowest level of automation. The vehicle features a single automated system for driver assistance, such as steering or accelerating. Adaptive cruise control, where the vehicle can be kept at a safe distance behind the next car, qualifies as Level 1 because the human driver monitors the other aspects of driving such as steering and braking. Level 2 is partial driving automation. This means advanced driver assistance systems or ADAS. The vehicle can control both steering and accelerating, decelerating. Here the automation falls short of self-driving because a human sits in the driver's seat and can take control of the car at any time. Tesla Autopilot and Cadillac Super Cruise systems both qualify as Level 2. Level 3 is conditional driving automation. A car itself monitors the environment using autonomous vehicle sensors and performs other dynamic driving tasks, such as braking. A human driver has to be prepared to intervene if a system failure occurs or other unexpected conditions happen. Level 4 is high driving automation. Level 4 implies a high level of automation, where a car is capable of completing an entire journey without driver intervention, even in extreme cases. However, there are some restrictions. A driver can switch the vehicle into this mode only when the system detects that the traffic conditions are safe and there is no traffic jam. Level 5 is full driving automation. Level 5 vehicles do not require human attention. The dynamic driving task is eliminated. Level 5 cars won't even have steering wheels or acceleration, braking pedals. They will be free from geofencing, able to go anywhere and do anything that an experienced human driver can do. Fully autonomous cars are undergoing testing in several pockets of the world, but none are yet available to the general public. Components of autonomous driving system. There are three main components of autonomous driving system, as you can see on the screen. LiDAR, known as light detection and ranging. The spinning thing you see on top of most self-driving cars is LiDAR. LiDAR is used to build a 3D map and allow the car to see potential hazards by bouncing a laser beam off of surfaces surrounding the car to accurately determine the distance and the profile of that object. It's also crazy expensive, hard to manufacture at scale, and nowhere near robust enough for a life of potholes and extreme temperatures. For examples: agriculture. LiDAR can be used to create a 3D elevation map of a particular land. This can be converted to create slope and sunlight exposure area map. This information can be used to identify the areas which require more water or fertilizer and help the farmers to save on their cost of labor, time and money. River survey. Water-penetrating green light of the LiDAR can be used to see things underwater and helps create a 3D model of the terrain. Underwater information of a river can help understand the depth, width, and flow of the water. It helps in monitoring the floodplains. Radar, it is known as radio detection and ranging. The radar units allow the car to avoid impact by sending a signal to the onboard processor to apply the brakes or move out of the way when applicable. Radars bounce radio waves around to see their surroundings and are especially good at spotting big metallic objects and other vehicles. They're cheap, reliable, and don't sweat things like fog, rain, or snow. Traditional radar sensors are used to detect dangerous objects in the vehicle's path that are more than 100 meters away. For example, military applications. The radar has three major applications in military. In air defense, it is used for target detection, target recognition, and weapon control. In the missile system to guide the weapon. Identifying enemy locations on the map. Air traffic control. The radar has three major applications in air traffic control. To control air traffic near airports. The air surveillance radar is used to detect and display the aircraft's position in the airport terminals. To guide the aircraft to land in bad weather using precision approach radar. High-powered cameras. The actual camera technology and setup on each driverless car varies, but one prototype uses cameras mounted to the exterior with slight separation to give an overlapping view of the car's surroundings. It is great for spotting things like lean lines on the highway, speed signs, and traffic lights. Some developers think that, with better machine vision, they can use cameras to identify everything they see and navigate accordingly. For example, monocular camera. A monocular camera refers to a camera that we often see daily. Monocular cameras are the mainstream camera that can be used as a monitor function. Stereo camera. Stereo cameras can capture depth information more accurately. It is necessary to extract the depth information of the shooting scene accurately. Illustrative example. These are some companies of autonomous driving system. Waymo, NIO, BMW Intel FCA, Daimler Bosch, General Motors, Volkswagen Group, Honda, Ford, Tesla, Intel Mobileye.